Yeah, I hope my talk can give you guys a taste of Web3 security. So my name is Peiyu Wang. I'm a security engineer. So what I do is application penetration testing, mostly Web3 applications, apps and wallet. And I also do smart contract audits and security research. My past talk at DevCon are the blockchain village, which I talk about exploiting crypto wallets and DeFi scam and rug pulls. So outside of like work, I'm like a DeFi apes, I'm like a meme coin traders. So blockchain and the apps. So since the first DeFi summer in 2020, the blockchain ecosystem has exceptional growth. There's a lot of things being built. And one way to catalyze them is like applications, develop tools, infrastructure, and protocols, which is the blockchain itself. So we're AppSec village, and let's talk about applications. So the most common AppSec heavy Web3 products are the following. The first one is centralized exchanges, such as like Coinbase, Binance, which you guys are probably familiar with, and then data platform. So the raw data for blockchain transactions are extremely hard for people to read. So there's like application like EtherScan that help people to like read data, read transaction data. And there's a wallet. So wallet is a type of applications that holds the private key and perform the signing request when requested. The most popular wallet probably is the wallet MetaMask. And then there's the apps. So the definition I give the app is a wide range of applications that include the functionality that implements through the on-chain smart contract. So all four type of applications plays a very important role in the application space in blockchain, and they all have their own unique type of services. Today I will talk about the one for the app. So throughout this presentation, I will be talking about a lot of Web3 terminologies. So I want to start by explaining them in Web2 terms. So first, smart contract. Smart contract you can think of it's a backend API server. Privilege functions. So inside smart contracts, there's a lot of functions. And some functions can only be called by, say, admin or owner address. Those functions typically actions, operations in the smart contract. And then there are transactions. Transactions, you can think of it's like a bundle of post requests that's sent to the smart contract. Transaction hash is a unique identifier for each transaction where you can pull the transaction information out by using the transaction hash. So gas. So imagine a web server that charges a certain amount of fee for post request. That's like the so each blockchain transaction will charge some sort of like crypto assets. And when there's a lot of people sending this like post request to a smart contract, the more you pay, the faster your transaction will be executed. So blockchain is formed by like a block by block, and each block you can think of it contains multiple like post requests, and then each block has like set amount of time in between. You can think of like batch of post requests get executed like block by block, and there's a certain time in between. So blockchain RPC is the communication channel that exposed by like blockchain nodes, so the outside entity can talk to the blockchain. And NFT is type of like digital assets that inform of image with ownership information stored on blockchain and image data and metadata stored on blockchain. So this is like a general workflow for the app. The app you see there is Uniswap, probably most popular and most used app. So you go to the website, there's like a connect button, and you click that. That will triggers a connection request pop up from the wallet. And if you trust the application, you can click next so that your wallet is going to connect with the app. And after connection is established, you can start using the app. In this example, I exchanged 0.01 Ether to 24 USDT, and I can click the swap. And that transaction gets sent to the extension wallet. And once you click the confirm, which means you sign the transaction, and that transaction will be sent to the blockchain and execute. And then that transaction will get executed, and the token will be swapped. Next, I'll talk about the architecture. So this is standard Web2 applications where you have like client-side app, and then you have like server-side components, like web server API database, which everyone familiar with that. The apps I put into three categories. The First one is API-less Dapp. What it means is the Dapp on the server side, there's no API. There's just static HTML JS file, and the main logic is inside the smart contract. So, for example, the example I give Uniswap, the early day version of Uniswap is like API-less Dapp, where the token exchange information is calculated by a smart contract, and the front end just help with user interactions. So this type of Dapp, the attack surface or the application side is quite limited. And this type of Dapp typically built with the React framework, and React has sort of SSS built-in protection there, so it's hard to find success there. And then unless you have you can completely take over the site by say using DNS hijacking, the application side, the attack surface is very limited. And typically when this kind of application gets exported, it's often the vulnerability from the smart contract. Now the second one is API-enabled Dapp. So compared to the last one, this one on the server side has a service APIs. And one example is NFT creation Dapp. So the server has API allow users to upload images or NFT metadata JSON to the backend. And then the backend going to return a URL. And you can use the URL to talk to the smart contract to create NFTs. The attack surface for this type of app does increase, but the vulnerability on the application side is mostly Web2 related. And now move to the full-scale Dapps. So full-scale Dapps, the backend is going to talk to the smart contract, read data or send transactions. So oftentimes in the full-scale Dapp, the smart contract will have privileged functions, and the account that can call those privileged functions, those private key are stored in the backend server. So if you have a way to say, for example, compromise the server or have trigger some arrow, you're likely able to say obtain that key from the server and completely transfer out all the money from the smart contract or cause very big damages. So the majority of the app in 2024 are a full-scale Dapp compared to 2020. By summer, there's a lot of API-less Dapp. So one example of a full-scale Dapp is cross-chain bridge. So cross-chain bridge allows user to transfer to bridge token from one blockchain to another. For example, to bridge token from Polygon. Because blockchain, the smart contract blockchain cannot talk to each other. With cross-blockchain. So this type of application must require a blockchain component. So how bridge work is on the source chain, user deposit token to a source chain smart contract, and the backend monitor that deposit event and process it. And if everything looks good, it will call the privilege functions in the destination chain smart contract and release the funds to users. So let's talk about Dapp threat modeling. So from a threat modeling perspective, in Web3 are the three following. First one is private key. If you can get those, you can have full control over the assets in the address, or you can invoke privileged functions in smart contract. The second one is signatures. So for certain type of tokens, if you can certain type of tokens, it allows other address to use the token if you can have the special message signed by the token's owner. And there's a lot of phishing sites that ask users to sign those type of message and then drain the user's wallet. The last one is API keys. So this API keys is for those crypto custodian systems, such as centralized exchanges or services like Peiyu. Once you get those API keys, you can take all money out from those services. So before I talk about I will start to talk about client-side attack by mentioning a term called already connected wallet. So in the Dapp workflow session, I talk about that if a user wants to use the Dapp must connect to their wallet. And there's a best practice in Web3 that users should only connect their wallet to the Dapp they trust. And then when users trust the Dapp, they just sign whatever things that Dapp want the user to sign. So if any vulnerability that exists, client-side vulnerability inside the Dapp that has a lot of user connect wallet, and it's very popular, the severity is going to increase like dramatically. So from a client-side attack perspective, there are like three things that attackers will most likely want to do. The first one is initial malicious transactions. How that can happen is when the attacker can basically modify the JavaScript code of the website. For example, through like cross-site scripting, hijacking, it's possible to have those malicious JavaScript to initialize the malicious transaction to take out all the user. And if injecting JavaScript is not possible, and if like HTML checking is possible, then another option is to deceive users to do something they're not supposed to do. The last one is redirect users to a phishing site. And for already connected wallet website, everything that can initial transaction will have critical vulnerability. So as I said, right, in Web2, even you have like account takeover, most of the time it's like high, it's maybe like a low critical, but in Web3, it's definitely going to be critical. So let's talk about server side. So from a server side perspective, there's like sort of like four things the attacker will want to do. The first one is stealing keys from the server. Right, so if you're stealing the key, you probably can with all the assets from the project, and there's a sort of a lot of ways can potentially achieve that. And the second one is stealing crypto assets from other users' account or admin's account. That will probably buy like broken access control or privilege escalation. Or you can spend assets more than your actual balance. That can probably happen like business logic error or risk condition. And for NFTs, as I mentioned, those like images are stored like on-chain. And if those images go down, those NFT value going to drop like dramatically. And that's what can happen when like so in Web3, anything that can touch this money will often has the critical severity. Because I think the most important impactful thing that can happen is removing stealing users' money. So in the last session, I talked about how Web2 attack vector have higher severity in Web3. In the next sessions, I will talk about what kind of like unique vector attack surface that can enable in Web3. So I think due to constraint, I cannot go over like each sub-item one by one. But in short, the applications that incorrectly process transactions, they can contain vulnerabilities. And it's possible to initiate attack against backend components through smart contract. And if the application handles the logic to handle different assets class is incorrect, it can also be attacked. So the first case I want to talk about is wasted crypto in gas via unrestricted APIs. So this application is a token redemption API that requires users to register wallet for participation. So how the registration workflow is there's a slash register API, which user can provide their own chain address, and then the backend is called a call. Yeah, so the finding here is that, well, that's amazing. So the APIs accept any Ethereum address as long as the address data is in the correct format. So each time the API is called, the backend going to send a transaction to the smart contract. And as I talk about, each transaction can cost gas. Gas is like, you can think of it as money. So the way to exploit this is like, I can generate a bunch of like a random Ethereum address and keep calling that API to let the admin wallet keep sending transactions to smart contract and eventually consume all the ethers in the admin's wallet. So this not only consume all the ether, but allow like and prevent like other user to register. So this is like the transaction log when I do the testing. So this is in the test net, so there's no actual like assets lost. So I write a script to generate a bunch of address and put the request into like be repeater and then just send it. And then when I go to Etherscan and I see those like records. The second one is poor transaction time handling lead to denial of service attack. So this can actually happen in any DApp that have API to trigger the backend to send a transaction and keep the connection open while waiting for the on-chain transaction execution results. So the example code snippet is I generate using like ChatGPT. So it's basically an API called deposit. And when user call this API, it's gonna trigger the backend to send a deposit transaction to the smart contract. And the code will wait for the transaction executed and then send HTTP response to the users. So what's the problem here is that, for example, on Ethereum mainnet, the block time is 12 seconds, which means the HTTP connection will remain open for at least 12 seconds. If the chain is congested, it can, the time can be much longer. So to exploit these APIs, only one single machine is required to send out a bunch of API requests and to occupy all the connection slot, and the server is not going to handle any more requests. The next one is pool transaction time handling lead to race conditions. So this is gaming, like a gamified Dapp that allow users to purchase in-game items using crypto assets. So deposit workflow by user deposit crypto assets into the game smart contract, and then backend retrieve those deposit informations from the smart contract to increase the user's in-game balance. And what's the interesting part is the withdraw crypto workflow. The withdraw workflow work by users submit a withdraw API request to the backend, and the backend verify the user's balance and call the privilege function withdraw in the smart contract. And after the transaction finished, the token will arrive in user's on-chain wallet, and the backend is going to update the user balance to 0. So what's the problem here is that the backend update the user balance only after the transaction successfully executed, and it didn't log the transaction balance when they send the on-chain transactions. So for example, in Ethereum, 12-second block time, users have 12-second window to spend their in-game currencies. So they can basically, in those time periods, they can buy 100 worth of in-game items, and then wait for the transaction to finish, and those tokens will be arrived in their wallet. This way, the user can basically purchase all the in-game items for free. And the race condition can also happen in Web2, but the time window for that in Web2 is much smaller. But in Web3, the time window in this case is at least 12 seconds, so it's much easier to pull off. The next one is bridge backend, lack of smart contract address validations. So I talked about how bridge work briefly, previous slide. So for this particular bridge, the workflow is user deposit tokens into smart contract on the source chain and obtain the transaction hash. And then the user submit the transaction hash to the backend through APIs, and the backend fetch the information with the transaction hash to validate the deposit. And if anything goes correctly, the bridge backend is going to call the privilege function in the smart contract and destination chain and release the fund to the user. So for this kind of bridge, the backend actually need to validate a tons of stuff. And in that particular application, it need to validate, for example, the transaction status is successful, and you need to get the information of the deposit amount, the sender, receiver address. And if anything is not validated correctly, it can cause the bridge to become vulnerable. And in this case, the backend does not verify the smart contract that received the token is the one operated by the project. So to exploit this vulnerability, the test flow will be, I am going to deploy a malicious smart contract on the blockchain that basically share the same functionality as the legitimate smart contract, and I make a token deposit into that fake bridge contract and obtain the transaction hash, and then submit the transaction hash to the bridge backend through APIs, and wait for the bridge backend to process the hash. And because I'm missing the address validations, so he think the address is correct, and then it's going to release the tokens to the users on the destination chain. And when that happens, and after that, the user can withdraw his token sent to the fake contract because he has full control of that. And if this vulnerability gets exploited, all the tokens in the destination chain smart contract can be stolen. So the last case. So this is a lightweight crypto trading application where user can deposit assets and perform token swap. The backend use Fireblock as custodian services. How the deposit work is user requests a deposit address through APIs, and then the backend gonna get one from Fireblock, and then the user gonna deposit crypto asset to the address. And then the backend periodically query the fileblock.getTransaction API. And if it sees the deposited transactions, it's gonna give the user the in-app balance. So when we are doing the testing, so we deposit like 0.1 meta token to deposit address, and the balance increased by 1.1. Like we were so confused because this is not like double or 10 times. It's like increased by 1. So we go to the on-chain, the Polygon scam, and see there's only like 0.1 matic arrive in the address. However, we found a record of like a scam NFT airdropped into that address. So it's quite common for scammers to airdrop like NFTs with like phishing site link in the token information to a newly active address within the blockchain. Newly active address means the address like received like a crypto with value for the first time. So the backend treat that valueless NFT as a valid like a MAT deposit. So this is a white box testing, and we found out the root cause is that the backend just when it parsed the information returned by Fileblock, it failed to check the token type. So to exploit these issues, we deploy a ERC1155 NFT and make 99 NFT with no value to the address, and which caused our account to increase like 99 matic. So to summarize the state of like Dapp security, so right now with the advance of like blockchain ecosystem, Dapp become like more and more complex, and some of them start integrating heavy Web2 components. And often vulnerability are introduced in Dapp because a lot of the developers they either lack of Web3 security knowledge or Web2 security knowledge. And Web2 vulnerability in Web3 application often has like increased severity because it can touch monies. And unlike smart contract export, where it's like publicly viewable, the exploitation of the backend might have less exposure because no one can see it, but it can still happen. So to secure a Dapp, especially a Dapp with like heavy backend components, it is like as important to get penetration testing compared as like getting like audits for your smart contract. This is the last slide. So if you want to get into a Dapp hacking, I would suggest like you first be decent at Web2 application hacking, because at the end of the day, there's tons of Web2 components, and you need to be familiar with the architecture of different type of Dapps. That way you will know what the attack surfaces are for this app, and the best way to do it is play around with Dapp to experiment them. An investment of like $100 of crypto, probably gonna waste in gas, is gonna be enough. And to understand like basic concept of blockchain, including those like Web3 terminology, you don't really need to understand how blockchain work. And then you learn the Solidity smart contract language so you can understand smart contract, and sometimes you can find some like hidden attack surfaces. And it's not necessarily require you to know like how to do a security audit of smart contract. That's a completely different topic. And go find a Dapp and hack it legally. And start like, and so I believe like starting hacking Dapp is probably one of the best ways to for like Web2 website hackers that pivot into Web3 security. And well, if you want to ask me like why like Web3 security, I mean like look at this bounty like 10 millions. Well, I don't think this can ever happen in Web2. So yeah, I guess people love money. All right, so that's my talk. I hope you guys enjoy and learn something about Web3 security. Thank you.